Well, in the series of lectures on probability distribution functions, this lecture is the logistic distribution. Today I will be spreading some light on the logistic distribution, logistic probability distribution. You can find there are many processes. There are many processes you can find that the growth is slow at the beginning. Okay, the growth is slow at the beginning and picks up in the middle and slows down again when approaching a saturation point. When this type of model of growth is a matter of concern, then in the continuous probability distribution, there is logistic probability distribution. We can use the logistic probability distribution in population growth. We can use it in market share of a new product, market share of a new product. In both the cases, that is the population growth and market share of a new product, you can find that the growth is slow at the beginning and picks up in the middle and slows down again when approaching a saturation point. Logistic distribution has a location parameter and a scale parameter. You must remember that logistic distribution has a location parameter and a scale parameter. It is as the normal distribution curve. The logistic distribution curve mostly similar with the normal distribution curve, but tails are more flatter. Tails are more flatter. Now, look, as I have mentioned, that logistic distribution is a continuous probability distribution in probability and statistics theory. And there are the probability density function and the cumulative density function. The logistic distribution is mainly used because curve has relatively simple cumulative distribution formula to work with. Here, the PDF probability density function of logistic distribution. This is the E, it has a number, and S is the scale parameter, and X is the random variable, and mu is the location parameter. Okay, this is the PDF of logistic distribution. The value of X lies between minus infinity to plus infinity. Clear? And this is the cumulative density function, CDF, of logistic distribution. Okay, so it is 1 by 1 plus e to the power minus x minus location parameter by scale parameter. The logistic distribution is the logistic distribution with the parameter mu equal to 0 and s equal to 1. That is, the location parameter is 0 and scale parameter is, and the scale parameter is 1. The mean of the standard logistic distribution is 0 and the variance is pi square by 3. Okay, pi square by 3. You can have a picture, then you can have a clear idea. Look, this is the PDF of logistic distribution, and here location parameters are not same, but the scale parameter is 1. When the location parameter is -1, then you can find this type of logistic distribution curve, this dotted line. Okay, this dotted line. And when the mu, that is the location parameter, is 0 and standard deviation is 1, then the solid line is the curve of logistic distribution. And when the location parameter is 1 and standard deviation is also 1, then the dashed line here, the dashed line is the logistic distribution curve. Okay. Again, this figure shows the distribution have different scale parameter but same mean, the location parameter. The location parameter is 0, but when the standard deviation, when the scale parameter is 1, then this dotted line is the logistic distribution curve. Okay. It is Skinner. It is Skinner. The curve will be Skinner or flat depends upon the scale parameter. Okay, depends upon the scale parameter. Here you can find when the scale parameter is 2, then when the scale parameter is 2, then this line, the solid line, is the logistic distribution curve. Is the logistic distribution curve. It is more flat. It is more flat. It is, you can say it is flatter. Okay. When scale parameter is 0 and location parameter is 0 and scale parameter is 3, then the logistic distribution curve would follow this dashed line. It is much more flatter. It is much more flat. Okay. So there are 3 distribution of logistic probability distribution curve depending on the variation of scale parameter. In my previous slide, you can see here the location parameters are not same, but the scale parameters are same. And so And so there is a change in location, but there is no change in scale. Now, suppose there is a badminton player. Look at this example. Suppose there is a black badminton player, and the badminton player, if if the player serves with high velocity, then there is a chance of winning. There is a chance of winning. And when there is at the same time, and at the same time, when the player serves, there is a chance of less accuracy. So at that time, he may lose the game. Okay. So when there is a velocity, high velocity, and there is chance, and also there is a chance that opponent could not protect the serve, then the player will score, and in that case it will get the point one. But when there is a velocity at the time of high velocity at the time of serve, and there is less accuracy, there is a chance of lose of the of that particular player. So then the score is 0. So linear relationship between the point conversion and the serve speed is there. So there is linear relationship between the point conversion and the serve speed. But also there is an optimum speed. The optimum speed, if you look at this logistic distribution curve, this bold line, solid line, if you look at this logistic distribution curve, then you find that the optimal speed is the mean, the location parameter. The location parameter. When the badminton player serve with high velocity and maintain it for a long time, then the logistic distribution curve will be flat, will be flat. And it will be more fatty. It will be more fatty rather than skinner, rather than skinner. If the badminton player serve with high velocity but less accuracy, is there, then the curve will be skinner. Then the logistic distribution curve will be skinner. So this is an practical example by which you can understand the logistic distribution curve. There is also there is also a there is also a suppose you look at this curve. Suppose this is a point. Suppose this is a point, and along this axis we measure the average speed of a badminton player, average speed of a badminton player, and along the vertical axis we measure the probability of the average speed of the badminton player. And if the player do not have a great serve, then this point will indicate such type of situation. Okay, such type of situation. But when the badminton player has a great serve, then it has a more spread up PDF. More spread up PDF. As much as the serve is great, the logistic distribution curve will be more spread up PDF. Will have more spread up PDF. Okay. So in this lecture, I try to clarify the logistic distribution and what is the shape of the logistic distribution curve and why we are using this curve. And here also I try to place in front of you a practical example with a badminton player. And now look at this slide. This slide shows different location parameters with different scale parameters. When location parameter is 0, that is mean is 0, and standard deviation is 1, then this is the logistic distribution curve. Okay, this is the logistic distribution curve. When mean is 4 and standard deviation is 2, then this red line will be the logistic distribution curve. Will be the logistic distribution curve. When mean is 8, here with S scale parameter is equal to 3, then this green line is the logistic distribution curve. So from this picture you can conclude that if the scale parameter increases, then the curve will be more fatty. The curve will be more fatty. And if the scale parameter is low, then the logistic distribution curve will be skinner, more skinner. So this is the this is the presentation on the logistic distribution curve. So I hope you got a little understanding over this concept and you have clarified the basic understanding of the logistic distribution, logistic probability distribution. Thank you for enjoying this lecture.